Welcome to the video for separable differential equations day 2. In this video we're going to focus on one particular differential equation that pops up in lots of different scenarios. And first we're going to derive it using separation of variables, and then we're going to use the results of our finding. So let's get to it. Alright, so this has to do with the law of exponential change, and very often in nature or in banking we'll see something that says something to the effect of the rate of change of a quantity is directly proportional to the quantity itself. And so the way that gets phrased is the rate of change of quantity is directly proportional to the quantity itself. And this differential equation pops up so much that once we've derived it and found the general solution or one of the possible solutions to this equation, we're going to use our results pretty regularly. So let's first derive it. And what we have is the first step that we should do is separate the variables. So we're going to go ahead and do that, and we get the y to the left side, and there is no t, so we'll just leave that constant over there and put dt. From this we wish to integrate both sides, and on the left side we get the natural log of absolute value of y is equal to kt plus c. And now we want to go through the process of solving this for y. So the first step I'm going to do is exponentiate both sides. And then I'm going to bring that constant, separate it from the e to the kt until I have, we'll go with big C e to the kt. And we don't know whether this big C is positive or negative, so the absolute value can actually be stripped away, and what we have is y equals ce to the kt. So what we can say is anytime we see this differential equation up here, we can just immediately jump to the solution y equals ce to the kt. And this is kind of useful to us because this shows up lots of different ways. You might be familiar with it being expressed as the PERT formula with banking, where you've got your principal and your interest rate. That's kind of the one that you may have seen in pre-calculus. So we can extend this. It doesn't matter what the variable is. If we had like dA dt equals k times a, then we can extend that to be that a is equal to ce to the kt. And c stands for the initial amount that you start with. So a lot of times with we're given an initial value in our initial value problems. So let's use this concept. We should be working to memorize this. Memorize, because it would be a burden to have to derive this every time we are given this differential equation. But if you memorize this relationship, you can bypass that whole deriving process. Let's jump to applying it to some problems. Okay, the population of bacteria in a culture increases from 400 to 1600 in 3 hours. And assuming the population grows according to this differential equation, we need to find the value of k. So we have the differential equation that dp dt is equal to kp, and because we memorized this off of the very first derivation, we can immediately jump to say that population is initial value e to the kt. And now we have an equation describing the population growth for the bacteria, and we can use our information to solve this for k. So what we have is the population started at 400, and after 3 hours it jumped up to 1600. and we have a exponential equation now that we can solve for k. So divide the 400 across, and what we get is a 4 equals e to the k3, and take the natural log of both sides. Natural log of 4 is k times 3, and finally we get the answer that we're after, that's ln of 4 divided by 3 is equal to k. So we now know the exact value of k. If it asks for an approximate value, we could turn to a calculator and get approximately 0.462. Part B, they asked us to find how fast is the population growing when the population is 3,000. Well, now that we know our value of k, we can write that in there. ln of 4 over 3 times population. And in this case, the population of interest is 3,000. So we're going to plug that 3,000 in right there, and we get ln of 4 over 3 times 3,000, and that is roughly equal to 1386.294 bacteria per hour. So at the time when our population is 3,000, we're growing by approximately 1,300 bacteria every hour. So that's a pretty straightforward example. It's important that we start with the differential equation they give us and immediately jump to this process so that we can avoid the whole derivation. Let's take a look at example 3. The amount A increases at a rate proportional to the current amount such that dA over dt, where t is measured in hours. If the amount triples every 11 hours, find the value of k. So right away, they give us the differential equation, dA dt equals ka. So we should be able to jump to the fact that a is our initial value, e to the kt. And now they want us to find the value of k. Well, they tell us the amount triples every 11 hours. So if I happen to start with 1, after 11 hours, I would be 3 times as big. And this enables me to solve for k. Divide and exponentiate, and we get ln of 3 is equal to k times 11. And finally, ln of 3 over 11 is k. So that's the k value that we're looking for. And they also ask for the 3 decimal approximation, so we can write that in here as well. Turn to our calculator. K is approximately 0.09987, and if we do the rounded or truncated rule, truncated is the 0.099, and rounded, the proper rounding on this would be 0.100. Okay, let's head on to example 4. Radium-226 loses its mass at a rate directly proportional to its mass. So they don't give us the exact equation, but we should know that the equation still follows the rate of change of mass with respect to time is directly proportional to its mass. So this is just saying it in words, which means we can jump to our mass equation. Mass is equal to the initial value e to the kt. So there's a solution to the differential equation, and now we should start working at applying some of the information that we have. They tell us that the half-life is 1,590 years, which basically means if I started with 100 milligrams, after 1,590 years, I would have dropped to 50 milligrams. So a very, very slow decay rate. And we want to solve for that k. So we're going to take the 100, and we get 1/2 is equal to e to the k times 1590. and natural log of both sides, and divide the 1590, and we get our k value. Which means our equation, if we write it out, for 100 milligrams would be 100 e to the ln of 1/2 divided by 1590 times our variable of t. I'm going to zoom in on this and talk about this equation here. This is a perfectly suitable equation, but there's several different variations that we can do with this equation. We can change the ln of 1/2 to be separated. Suddenly jumped. Okay, separated from the other pieces. So times t to the 1590, or t over 1590. And then we see that combination of the e to the ln, and those can cancel so that our mass could also be expressed as 100 times 1/2 to the t over 1590. And this format is a little bit more in line with ways that we have talked about exponential growth in the past. We have our initial value, and we lose 50% over the time of 1,590 years. I'm going to throw one more in here just because it's useful to see lots of variations of this. We could have a negative t ln of 2 all over 1590. So that 1/2, ln of 1/2, is the same thing as ln of 2 raised to the negative 1, which is the same thing as negative 1 times ln of 2. So that log property was used to arrive there. So it's important to know that a lot of these exponential expressions have multiple ways that they can be expressed. So when you're tackling it as a multiple choice problem, you can see the different possible answers that might exist. Anyway, we have our equation now, and we want to move on to part B. How many milligrams of the original sample remains after 100 years? So this is just asking us, what is m of 100? How much exists after 100 years? And we can use any one of the equations that I found. I'm going to go with the one that I think looks the cleanest and plug it into that equation. And we find that that is approximately 95.734 milligrams. If you plugged it into the one that we found first, you get the same answer. It's just it takes a little bit more time to write out that process. Okay. Finally, after this part, we asked one last question, which is, how many years exact answer will it take for the sample to have only 3 milligrams remaining? So we can use the simple equation of the 1/2 raised to the t over 1590. And this is not the only approach, but I think this is the easier equation, so it's the one that I prefer to use. If we divide the 100 across, we get 0.03 equals, I'm going to write this in decimals, 0.5 to the t over 1590. If I take the natural log of both sides, ln of 0.03 equals t over 1590 times ln of 0.5. And then we're going to isolate the t, and that will give us the answer. So we get ln of 0.03 divided by ln of 0.5 times 1590 equals t. So there's our answer. That's the exact answer. I think it's useful to also find the approximate answer, and if we did that, it winds up being roughly let's see, 8,043.641 years. A very long time indeed, but it kind of makes sense. 8,000 years, that's about, I don't know, 1, 2, 3, 4, 5, about 6 cycles of half-life, maybe a little bit more. And if you thought about this, we go from 100 to 50 to 25 to 12 and a half to 6 and a quarter to 3.125, I think. And that's 1, 2, 3, 4, 5, 6 cycles. If I did that right. 50, 25. Sorry, it's actually 5 cycles. And this is roughly 5 times 1590. So, looks pretty good. These rough checks are, rough, but worth taking a shot at when you can do them. Anyways, let's move on to example 5. 5 and 6 are fairly quick examples, I believe, but slightly different from this CE to the KT formula. They're more in line with this format that we've got going on. So let's take a look at them.
You know what to do with that big fat butt. Wiggle, wiggle, wiggle. Wiggle, wiggle, wiggle. Wiggle, wiggle, wiggle. Just a little bit of patty cake with no hands. Got me in this club making wedding plans. If I take pictures while you do your dance, I can make you famous on Instagram.
Right, suppose the amount of oil pumped from one of the canyon wells in Whittier, California decreases at the continuous rate of 10% per year. After how many years will the well's output fall to 1/5 of its present level? So what we have here is we have some volume that we're trying to look at, and we're going to say that we start at 100%, and every year we lose 10%. So we're multiplying it by 9/10. So we're going to get 90% after 1 year. So you could think of this as t divided by 1. So this equation tells us what is our volume after each year. And we can plug in 1 and we'd get an answer of 90%. And then we can plug in 2 and we're going to lose 90%. Sorry, we'll lose 10% of the 90, and so on and so forth. And the target is for us to find when is our volume 1/5. And 1/5 is pretty easy to consider as 20%. And we continue this thing out, and we're trying to solve for the variable t. So when we divide the 100 across, we get our, hey, there's that magical 1/5 showing up. 1/5 is 9/10 to the t, and we want to solve for t, so we're going to take the log of both sides. We get the natural log of 1/5 is equal to t times the natural log of 9/10. And very quickly here we can find the time that we arrive at 1/5. So we just divide that across. And again, here's a exact answer that is very useless to somebody who's running practical answers. So we get the exact or the approximation, and it looks like after 15.275 years. So that means we start at 100 and then we're down to 90, and then it looks like if we lose 10% again, we're going to drop to about 81, and so on and so forth each year. And then after about 15 of these cycles, we finally are down to 20% of our the amount of oil in the canyon. All right, one last example, example 6. Another approach that we can take with these problems is what we do is we start with our equations that we might know from the data given. And one of the equations is that the population, we'll go with the population, we'll just use this model, the initial value e to the kt. So we're going to use that population, and we don't know the initial value, but we do know that there's two different possibilities, one where we wind up with 300 population and one where we end up with 100 population. And it takes 4 days to get to the 300, and it takes 2 days to get to the 100. So what we have here is two equations, and we want to use those two equations to find what C is. So first off, it looks like we have two unknown variables. We have the unknown of C, and we have the unknown of K. A pretty fancy trick that we can do, if you might recall from our pre-calculus years, is we can divide the two equations. And if we do that, what happens is the C's cancel, and the K4 over K2 becomes e to the K times 2. And now we have one equation with one variable, and we can solve that for K, and we take the natural log, and now we know what K is. But K was not our target. We want to actually plug that in to figure out what was C, what is our initial population. So we're going to plug this into one of our formulas. I prefer smaller numbers, so I pick my first formula, and I plug it in for the K value, ln of 3 over 2. So what we have is, after 2 days, our growth rate causes the initial population to become 100 fruit flies. Solving this out, the 2's cancel, the e to the ln cancels, and we're left with 100 equals C times 3. And solving this for C, we get the oh so strangely non-realistic case of 33 1/3 fruit flies. So in the perfect world, this model would predict that there's 33 1/3 fruit flies to begin with. But in a logical world, we would probably actually just say we started with 33 or 34 fruit flies. It's probably too hard to count 300 flies exactly anyways, because they're so small and buggy. Alright, so I kind of cruised through this video fairly quickly. A lot of this was review of exponential equations from our pre-calculus years, and as such I didn't go too in depth, but I did want to show the connection between differential equations and the exponential equations that we're familiar with. Ideally in class we'll be able to go over a few more examples and practice this with peer support. Anyway, thanks for watching, and have a good evening.